Good morning, everybody. For anybody that shows up, either, well, now or in the future, good morning. This is going to be my last stream of 2024 because I'm going to be going on a small 2-day vacation. All right. Well, I'm already on vacation, but like a vacation away from home. So this will be it until I get back. And then I plan on doing some more on either Wednesday night, Thursday, during the day and evening, and same with Friday. So in any event, let me get some music going here and talk about my failure. So I tried doing my sort of optimization last night, and I think I let it go for like an hour or two, and it never got past the first stone in the initial arrangement. And the initial arrangement, just to remember, it looks like this: 6, 7, 8, 8 stones. That's what you start with. So not that big of a deal, but it doesn't grow exponentially, but it it sort of feels like it's a sort of a doubling thing. So, if that makes sense, because you either are going to, if it's a 0, which isn't that common, you're just going to keep it a same stone. If it's an odd number of digits, it's the same stone multiplied by this, but it's still one stone. And the thing I was realizing is, in the worst case, if every time your stones split, I think, like, if you see after 25, you get 33 million. After 75, you get a gargantuan number. Now, of course, that doesn't happen because in this case, and that's just saying one stone. Even with 2, after 25, you only get up to 55,000. Okay. And what's interesting is the numbers on the stones matter in terms of the algorithm, but they don't matter in terms of the final calculation, if that makes sense. So in any event, I think what I have to do is a very extreme optimization. And again, I don't know if this is going to finish in time, but I've been trying to keep in the back of my head, is there a way to do this where you would have to do something where, how do I explain this? Yeah, I can't even explain it. Let me go back to my notes here. Let me back up. So let's say your initial arrangement was 2 stones. And it would actually make no sense for you to be able to get, you'll never have less. So actually all my numbers here don't make sense in terms of the algorithm, but at least it helps me keep in mind conceptually what's going to go on. Though I should change this to say, do something that makes more sense. Okay. I'm just trying to say if I get... If you're watching my stream yesterday, this stuff sort of will make sense. And actually this has to be like 3. Okay, so let's just say, for giggles, that this is what happens. I think what I need to do is basically say, here's the first stone. On its next iteration, it's either going to produce 1 or 2 stones. Okay. And then for each of those 1 or 2 stones, let's say that this one produced just this one here. This one produces these 2 stones. Okay. Now let's say this one, what does it do in the next iteration? Well, it actually produces 2 stones. Okay. And those 2 stones would each create, this one creates this one, this creates this one. Well, my point is that you just look at a stone and you do the production of either 1 or 2 stones with their new values. And then you say in the next iteration, well, what do those produce? So it's kind of like what I have here, except the initial one, we get all the stones, and then we get, well, here's the seed. Now the seed, though, is not going to be captured in a stones array. We're going to just say, here's the seed. I'm either going to get 2 or 1, right? And then the iterations here to say 5, we're going to say that's 1, I believe. We already have test cases that we can tweak this to see if it's going to be 1 or 0. But if it's, if the iterations is 1, then we're going to return, in one of these cases here, like in this case, we'll return 1. In this case, we'll return 1. In this case, we'll return 2. Okay. Otherwise, we have to do the math and then say, go get the stone for this stone. So, do I have all this more day 2, more part 2, day 11 work need to keep going? And so, yes, I'm making a stack frame, which is a meg, for every recursive call I do. But this also makes it so that you don't have these arrays that just keep getting bigger, and you just follow down and move over as slow as you can, trying to keep it so that you don't end up having too big of an explosion of stones, for lack of a better term. If you get 1, if you start with 1 and you get 2, well, you're not going to do the second one until the first path is complete. And if the first path makes another one of 2, fine, now you got 5 stones. Well, you're still going to do the first stone. Maybe that just makes 1, and then you'll make 1. So you're trying to keep it very tightly bound to just that. If this doesn't work, I don't really know what else to do. So if you're watching, maybe you have an idea. And if you're watching and this is your first time on the channel and you haven't subscribed, please do so. I would greatly appreciate it. Trying to get to that magical 1,000 subscriber marker to start. Okay, so we're not going to do that. We're not going to do that. And we're not going to do that. We're not going to do that. And we'll change this to stone because that's what you're actually getting. If the stone is big integer 0, now we can say here if iterations is equal to 1, we're going to return 1 because you're just going to make another stone. You don't even need to make the calculation because you don't care about the number. Else, we're going to say stone is equal to that. And then we're going to return get stone count with, actually we could just say big integer 1 iterations minus 1. We don't want to do minus because that would think would happen on a postfix. So We can just say stone here, be consistent. Okay. Now we determine if I think this is correct. I'm not entirely sure though. Here we're going to determine if we have odd or even digits. Again, if we have, we can't just return 1 or 2. We have to do the logic in each case to say, here we'll return 2. And actually, we don't even need to do an else here. Okay. So we're going to return get stone count of the quotient iterations minus 1 plus get the stone count of the remainder iterations minus 1. Else, and if we hit this case, we do this. Otherwise, we're going to say it's this, and we're going to say go get the value. Oh, yeah, duh. And so I think, all paths will return a value. And so we start by saying, well, here's a stone. We're going to start with 25. Otherwise, we do that. And the stone count would be the 2 then. Right? Because you got to do one and then you got to do the other. Now, does this pass our tests? It does. Okay. Well, that's encouraging. Let's do that. And let's see what we get for that. We get through them sort of quickly. 228, 668 is the right answer, I believe. Yep. Let's just throw in a 30 and let's see what happens. Pretty quick. What about 40? See, now it starts getting a little slower. What about 50? Yeah, and we're back at square one. It's taking forever now. I mean, you can't hear my computer, but it's taken off like a jet. So that doesn't help. Well, this might be a very short stream because that was my only really idea, I guess. At least we know that this also works. We just can't get, once you get to too much, it can't get past a certain iteration size. Is there anything to do here to be clever? One would be the idea that you throw each calculation in a task, but that has a ton of overhead. You could put each original calculation in its own thread. So if we did that, our stone count tasks is equal to a new list of tasks. Task.run. We can take out the index now and take that out. And then we can say stone count tasks wait. Oh no, task wait all. And then this the stone return stone count tasks sum of okay, I'm doing something wrong here. Waits for all the provided task objects to complete execution unless the wait is canceled. But what I want is the results of all the tasks running. That's not it. And I'm just being stupid. Get await or get result. Okay, I'm being stupid. Task wait all. Yeah. Getting return. Right. But there is no result here. Oh, yeah, I'm being stupid. Oh, hint. There we go. There we go. I was just being stupid. And so we don't need stone count anymore. Do these all still pass? They do. What happens when we go back down to 25? Well, pretty quick, but as we know, it's going to get slower and slower. I mean, I could just let this run and come back in 2 days and see what the result is. But I'm missing the optimization that you need to really make this fly. Though I don't see how you can... You have to figure out, do you make one stone or two from one stone? There's no way around that. You have to do that. Oh, yeah, that's great. That's cute. Okay, so we know that get stone count has to be something like a big integer. Although it did come back. Okay, you should be okay now. You should be okay now. Why are you... Cannot... Supposed to be big integer to long. You know... You had it. Come on. So. Yeah, so how do we... I mean, whatever works, right? And this should still, for 25, it comes back awfully fast. For 40, There's a little bit of a crawl for 45. Yeah, it's like it just whooshes. And that's a technical term, whoosh. I'm wondering if is there something some optimization that I'm missing? Obviously I am. So that the calculation can be sped up even more. I don't see how though. And that's my fault, if anything. I mean, part of me is thinking I have optimized this as much as I can. And there is no more optimization to do. Well, this might get done quicker than I thought. I could let it run for 75. I have the feeling, though, that it wouldn't finish in any meaningful amount of time. Like, let's play with this. So we don't want to do 75. Let's do 25. 25 takes 2/100 of a second. It's really quick. Let's make some notes here. 25 yields. This is an answer. Okay. Now, let's bump it up to 30. Not too bad. How about 35? Now we're starting to see a pause. How about 40? If I could actually type. Now we're up to a second. .45. So you can see it just starts. Again, that's a technical term. That's 10 seconds. I wonder how good my elite Excel skills could be here. Well, it's 50. Anybody know any good jokes? 50 is about the limit in terms of what I would actually probably want to run here. What's bothering me is that this is one that I just can't figure out an optimization to. Yeah, it's taken off like a rocket ship. Well, a minute. I mean, it's not terrible. What's that from Chernobyl? Not great, not terrible. But you see, we went from 9 seconds to that. We're like getting closer and closer, but actually I can take that away from my day 11 notes because... All right, before I end the stream... I mean, I could move on to 12 because there's nothing to stop me from trying 12. But I would like to finish one before I move on to another, if only because I would like to do that. And the way that this is increasing, I could see this getting up to days to do 75, and that's just not right. There's got to be a way. I don't know. I really don't know how to optimize this. The only one thought that I just had is not to-dos. you don't want to necessarily like the thing that went through my head is common values. Single digit values would be pretty, like you see here with that. After 6 blinks, roughly half of them are this common value. Okay. And a 2024 is a common value. And so what I'm saying is if you hit a common value, you could basically say, I know that after 25 iterations, it's going to produce this many stones. And you don't need to, if you can get to 50, what you could say is then as, well, this would get back to the idea of doing it in chunks of 25. Which maybe what we could do is say for a given input of 0 after 50, what does it do? Because then what we could do is do 25 the original way. And get that seed of 25. Because that's going to be 55,000 stones. Well, no, it's going to be, for us, it'll be 250,000. Okay. But then what we can do is say if we're hitting some of these seed values for 50, they're pre-computed. We know what they are. We don't have to keep doing them over and over again. Unfortunately, the way I have it now, well, that's why we have Git. But the way I have it now is it's not going to allow me to do it because we can't, all we get is a count. We don't get the state of the values at that count. What we really want is something to say get stones after a certain amount of input. And if we have to get if we've got to run this for 10 values, that's 10 minutes. Meh. But then we're eliminating the need to do the same exact calculation over and over again. But again, we're only producing the count if we do it this way. So what I'm suggesting is for 50 iterations, what's the count for values 0 to 9. We could also do 2024 because that's one that could show up if you go back here, because you'll have a 1 here, but then it will go to 2024. A 2024, I believe, has common values of 20, 2024, and so these are some other common values that would show up. You know, as you're doing this. And 8096 will split to this, but then that's going to split right to 8, and those will go to... So we're trying to... This is just a guess, a pure, unadulterated guess. Let's put in 0 for 50. Okay. Oops, that's the wrong one. There we go. So we know this is going to take about a minute. But the thing we're hoping to gain is that if we get the list for, if we put in the code back to get a list for 25, and then we go through all their values and get the get their values. If we run into at least half of them where there's some of these pre-computes, then we don't have to keep doing that. So we'll say value count. And so this was 0, and that was the count. Because all we need is a number. We don't care about the value. What does 1 give us? And so these chunks that you're seeing here of 30 seconds, what my hope is that that's going to that will reduce the amount of calculations that we have to make. Because you can say, if we hit one of these pre-computes, we can say, we don't have to do 50 on this one. We can just let it go. You know, a little bit nicer formatting on this. So let's do all the values we want. Okay. I don't know if this is really going to help, because even when we get to 25, if we recut this in half, arguably, what would really be, I mean, these are what I consider to be like not primitives, but these seem to be the things that you eventually reduce down to, and then they start going off again. And so if you don't, the problem is that all you do is you get a count. You don't get what the actual stones are at that point. You just know this will, after 50, produce this much. And so maybe what we should also do is consider doing 25, because you could do 25, chop off half of that. Well, now you're going to have to go through each one and do its 25, but you could chop off half of that with the pre-computes. So we also want to do this for 25 iterations. And of course, we got to take these out because we don't know what they are. Actually, no, we can't do it for 25. The reason is because that would give us to what we get to 50, but then of course we don't see well, what we could do is say we do 25, and then for those that we chop, yeah, we could still use these values. We could say do 25, get the stones. For all the ones that have pre-computed 50 values, we can just say that's the sum, and we return that. Otherwise, for each one of those that are remaining, we compute its 25, and then we say, out of that list, which ones don't have, which ones are in our 25 pre-compute list, and get those sums. Otherwise, we use our current, our new way of just getting a stone count for 25. Because we know that for 25 is actually pretty fast for a given number. And yeah, that adds up if you got to do hundreds of thousands of them. But, you know, it's even when you get to a count of, as we saw here, 30, it only is 5/100ths of a second to get the value, the count for a particular value. So maybe this is the way to go. Is we do 25, we pick off the ones that we know we have a 50 pre-compute for. Then we, for those that we don't, we do another 25. And we pick up the ones we have a 25 pre-compute value for. And then the rest of them, we just have to get their values, which we have a fast way of doing. So it's a combination of all the things. We just have to laboriously get these 50 values. Once we get the 50 values, I think we're okay. All right, let's do 3. Got any good jokes? Read any good books lately? This is where I need to start at. I need to have a lot more people watching and be interactive and ask me all sorts of stupid questions. Nothing offensive, but just stupid questions. And like, why are you doing it this way? Why are you a moron? Because I am. But this should... Yeah, I'm going to have to do some clever coding here, but... Okay. Now let's do 4. Once I get all the ones for 50, then it'll go quick. The problem is that I don't have any tests. That's probably something I want to do here, is add some tests for this approach where the input's a little bit bigger, and that way I can, and then I could make this a test case, right? So let's actually do that. Oh, I can't. Oh, I can. Right? I could say iterations of 5 is 13. And so we want a long iterations, long expected stone count. And so I can say this is L, and that's L. And our, no, the iterations is an int, right? Yeah. So we can leave that as an int. And so we can say iterations here gives us that. And if we really wanted to, we could also put in the input and get, just run string in put, and then we could say, yep, expression bodied. And now we could just have multiple cases. Okay. So that was for that. Five. So we're going to want 1, 2, 3, because we have 10 and then 25. Okay. So now we have a more compact way of doing our testing. Okay, we got 5. This is oddly fun. And again, I don't think I'm even doing this as correctly as I can, but this is the only way I can think of to optimize it, is to use well-known compute values. And you can always add to the table. You can always say, well, maybe this is more common, you know, and say, pre-compute that and then put that in my table, so then I don't have to do that. Like, because again, even for a simple problem as this, you have to do 2 and 2 and 2 and 2 again. And if it's just a lookup of a table, you save tons of computing time doing that. All right, this was 6. It would be interesting later on to say, is this the right way to do it? I'm kind of thinking not. I'm kind of thinking there is a better way to handle the computation in a much faster way that I'm just not privy to in my brain. Are we actually playing? Oh, yeah, we are. I just had turned it down. Okay. So that was 7. What's 8? We're getting close. And then to do the ones for 25 should not be that tough. Those should be pretty quick. Has a lot of stones. And then 9. But again, if you think about it, what is this? This is a billion calculations that I no longer have to do if I run into a 1. All these are almost a billion calculations. And if you look at each list, and this is just, again, for this seed, it isn't a guarantee, but like in this case, if we landed on this being our stopping point, those are 5 stones that we don't even have to go past. If we ended here, that'd be 1, 2, 3, and we're going to do we do 40, 48? Is that what I said? Yes. That one, and that's it. This one, it'd be this one, all these, 2024, so no. These, this, all of these would not have to be done. So that's a lot of time saved. All right, let's do 20. Now, here's the funny thing with 20. It's 2 and 0, and you already have those primitives, but you have them for 50, not 49. I'm wondering if we could keep it the same way we have it, but say, like here, if the stone is a big integer, and either we hit 25 or 50, then we return the pre-computed value for 1. And we don't have to keep recursively going down. At every point here, if we get a pre-computed value for, well, yeah, for 50, we would know what it is. If we're down to 75, because we always subtract the iterations by -1, so as we're going down. So if we get to 50, we could quickly eliminate those. If we keep going and we get to a 25, we could completely eliminate those. Just thoughts. The intrusive thoughts are winning. Because that way you could say when we get to 25, we could keep this approach and eliminate a lot of the potentially a lot of work, and this wouldn't create a race. So that might be another way to do this. Lots of possibilities. Okay, so we want to do 24 now. Because yeah, once you Once you know it doesn't change. It's algorithmic, so we always know for these seed values how many stones would be created. And that saves us so much time in calculation. And yeah, they're lookups on a table, but you would only say if the iteration count is 25 and it's in the table. You wouldn't just try, you have to look it up first. If you're at these magical values, magical spots. So this stream is turning out to be a lot of like optimization ideas. So we have 2, 24, 40, 48. And that's the thing about this is that if we think we could find more like seed root values, like you could argue and say 40, 48 might be some as well. All of these end up saving time. And we can just add to them if we think there's value in adding some of these other ones. But preventing a search to go down to 50 is highly beneficial. So let me get, by the way, if you're new to the channel and you haven't subscribed yet, please do so. I would greatly appreciate it. I'm trying to get to the magical 1,000 number, so the more the better. I might just do those other 3. Because 4048 is turning into a pain, which isn't surprising if you think about it. I'm surprised I didn't put in 2024 here. We better be careful that we put in the right value here. Okay, so let's do 2024 now. Hey Jason, I stream any code modularity tips for beginners. Not sure what you mean by modularity. I mean conciseness. I'm just not sure what you mean by that. And we could also put in 40 and 40, 24 and 48. Well, is that true though? Like, I guess we could do a statistical analysis and say, like 2024 would get to 40, 48, and then you'd split this. Why would you get to 80, 96? That gets times there. 0 goes to 1. 2 gets times to that. Oh, a 4 gets times to this. Okay, so you're doing what the next value would be from one of the seed values. And what are we doing here? 2024. 2024 is that. Okay. And now we want to do 40. Doing the 25 one should be quicker. If I ever get the answer to this, I'll be very interested to see what other people have come up with in terms of optimizing this out. I mean, I could see in saying if you have one value and you compute as you're going through, But then that would arguably make your pre-compute table really, really big, and you don't want to do that either. And now let's do 48. And this will be the last one we do for now. At the 50 calculation level. Come on, get through your billion calculation nodes. The thing is, this is, I think, very computationally expensive. It's not size. Well, recursively, you're going through and figuring it out, so that does add some overhead that way. But okay, so now we've got all of our pre-computes for this, and hopefully they're all right. If not, I'm going to have to go back through them again. Now, let's flip it. Let's do 0 for 25. And these should be pretty quick. Let's do 1. Again, all these will help in terms of saving time. 2. There. Let's do 3. And I could do this probably a little easier than what I'm doing. There are lots of ways to organize your code for you, so best hope. Code organization structure often depends strongly on the programming language. That's true. Okay. What did we just do here? We did 3. Let's do 4. Don't want to rush this because these are important. We don't want to miscompute or associate the wrong values to something. So let's do 5. And now let's do 6. And there. Now let's do 7. And you can see all these are 100ths. These don't really save a ton, but every single one matters, right? Arguably, we could also say like any iteration value for running, we could pre-compute these for any iteration value if we're finding that that's helping. One thing I found really deceptive about day 11 is the problem very specifically says, yeah, the order. Yeah, you're exactly right, Daniel. It does throw in that restriction, but you're right. The order doesn't matter because basically the algorithm comes down to I have a stone. If I do the iteration, do I get 1 or 2 stones, and what are the values for those 2 new stones? And then I take a stone. So it's an iterative algorithm that just says I have a stone. What do I get for the next for the output? The order, like you said, literally does not matter. All right, let me stay focused here. Although I do like the commentary. That is good. I just want to make sure I do not screw these up. We're at to 9 right now, so let's do 9. Okay, we're going to do 20. Actually, we want to throw in 20, 24, 40, 48, 20, 24. And again, I have no idea if this is, you know, the right way to do this or not, but it is a way. Let's just say that. All right, 20 gives us that. Let's do 24. Gives us that. You know what I could have done is done all the values and generated the dictionary code that I need to set, but hey, didn't think that far ahead. 40 gives us this. What does 48 do? That, we're almost there. 2024 gives us this. And what does 4048 do? That. Okay, so we have our pre-compute table. Come on, switch. Of these values, okay? So I'm clicking on you. I'm clicking. There you go. In fact, one different approach is compute a value for each iteration. Just throw order out entirely. Yeah, I think I know what you're getting at, Daniel. By the way, you're not crossing it yet, but there is a fine line here to helping and giving me the answer. So I appreciate if I ask for help, or if I'm, you know, struggling and I say, hey, I'm a little clueless. Anybody got any hints? What I don't want is a full solution. So, and again, Daniel, you're not doing that. I get that. I just wanted to reiterate in general, if anybody's listening live, just don't blurt out an answer, because that misses the point. I want to struggle. I want to be on the struggle bus, but that's a different. I think yours will still work, though. I'm hoping it will. So let's put some compute tables here. So we want a private static read-only dictionary of the iteration count, which is an int. No. We need the big integer, because that's the stone value. Pre-computes 25 iterations. So we're saying if we're at 25, then I want to say for this number, how many stones do we get? Equals a new, except we want to put in some values. Jesus, go away. Not that. We want that. So 0. You can just say 0L. L. Yes, I can. And you're going to say, I'm not being used yet. You will be, don't worry. Oh, yeah. I guess I should have put a comma there. I think that's enough. 1 gives us this. Let's say 2, 3, 4, 5, 6. 8, 9. What's after 9? 2024. 40, 40, 48. 2024, 20, 40, 48. Okay. All right. Now let's make sure we got the right values here. 2 gives us this. 3 gives us this. 4 gives us that. 5 gives us that. 6. 8. 9. I mean, one thing I thought of is as you're computing all these, like I said, you could keep like a growing table, but that could get really out of hand in a hurry. And you want to be careful that you don't spin wildly out of control like that. Okay, let's just make sure that okay, that looks right. And then we need our pre-computes of 50. Shuns. Of course, this will be a little different. 0, slightly bigger. These are slightly bigger. Because the other values, like for 30, 35, weren't that slow, I guess what we could do too is like say, make a table for 30, make a table for 35. And again, you can just interject them in the way I'm doing this here. Okay. So if we get down to 1, we return a 1. Otherwise, if iterations is equal to 25 and pre-compute 25 iterations, try get value of our current stone value out var pre-compute. Return pre-compute. Otherwise, we got to do that. And now we can say the same thing here. We can say for 50 if we have it, and we got to go to the 50 one, not the 25 one. Pre-compute 25, just so we have a different value here. Pre-compute 50, we're going to return 50. Now we have to do this in the other spots as well. Actually, do I want to do it here, or do I want to do it right at the beginning? Is this right? Actually, okay, hold on. Let me do this, and let me comment this out. Let me come back to my tests here. And I want to make sure that I didn't screw anything up, okay? So this does not do anything with the pre-computes. This is just the way we've been doing it. Okay. Oh, what now? Fine, you know, stop being so needy. Okay, so I have no idea if we go up even higher what this is going to be, but we know actually we know something else too that we could do. So we know this is wrong, we just need to grab the right value for it. And now this should run. Why is it returning 0 for iteration? I'll get back to that in a second. Let me just finish this out. It does work. I mean, what I'm doing there does work, just because I am getting all the right values for stuff. I just I do want to answer. God, I hate that screen. I just want a couple more test cases to say when I throw in my logic for the pre-computes that I get the same answers. See, as soon as I click on that, it just zooms down. I'm like, why? Okay. And that's about as far as we want to go. Whoops. So now we get 6 passing. What happens, and I'll get to your question in a moment, if I put this in. So you're wondering why I have iteration 0. I don't know. That might be a holdover. That might actually be from something I was doing before that I don't need anymore. Because if I ever get down to 1, yeah, that's a good point. It's not really hurt anything because I never get there anymore anyway. So, yeah, I can just take that out. Small catch, but a correct one. Thank you. So now I can say if I'm at 25 iterations and my stone value is like a 2, I know what the result is. Same thing with 50. So now if I do this, it gets the answers. It gets the answers right. It was a little concerning how we're still doing like a number of tasks too, but that's okay. Let's go here and go back to doing 25. Let's comment this out and let's see what happens when we run this. We get the right answer. Let's bump it up to 35. 45. And we start to slow down again. But it wasn't that bad. Actually, if I say solution run of this file, and I say 45, let's just take out the 25, the 30, and the 35, and the 40, and the 45, and the 50. What is it like for 45? We're down to 5 seconds. What was it before? It really hasn't cut off that much. Not as much as I was hoping for. I mean, it did. It did cut down some. If we do like 50... It does cut it down. I mean, it's about 40 seconds, and before it was 70 seconds. So it seems to be having it. But 50 is also the point where we really are not getting any benefit from the 50 pre-computes yet. Right? Because yeah, the 50 be really fast. It would, but like, yeah, I think what I was just saying is what you're getting at, Daniel, which is it doesn't actually, we're not actually hitting the 50 pre-compute table yet. I mean, we are, but only for the first, the inputs that are in day 11, which are not many. We'd only hit this one and this one. The rest of them we still have to do. I think the real value is going to be if we start going up and see does it actually help. Hello? There we go. So let's try that. What happens if we do 55? You just go for all at 75. Potentially, yeah. Let me just play with this a little bit. You should see benefit from the free 50 pre-computes at 51. I should, yes. My point is that my last one was just 50, so we don't see the... Now with this being 55, we should start seeing some benefit. It's just a matter of how much. And we wait. Yeah, unfortunately, this doesn't seem like it's showing that big of an improvement. I just wanted to get a number back for 55. Okay, clearly good call. Just go to 75. Yeah. I even though I think we are saving a decent amount of calculation at this point, we still have to do a lot. I do think that these numbers all reduce to these common smaller numbers. Like you see 250 grows, 512 eventually gets split. 1030, this number is going to, well, that's odd. So that will still grow. But it does feel like there's this pattern of you start to get reduction down to smaller values. Yeah, we're still going. 55 just blows up. We're trying to find pockets and areas to reduce the amount of work as much as possible. Well, sadly, this is now turned into a black box because I don't know. I don't have any metrics printing out, like, and I don't even know how I could do that. Like how I could reasonably say where are you without cluttering up the console window beyond all measure to say, you know, a whole bunch of data that it can get. Well, I still don't think this is the solution. I mean, I think it's obviously better because you could see here for 45, it was taking about 10 seconds. It's now taking 5. For 50, it was taking a minute and 12 seconds. It went down to about 40 seconds. But of course, we didn't actually get the benefit of the 50 pre-computes. We only got the benefit of the 25, and that was it. And you can see here, we're still running day 11. So I'm sorry, we're still running 55 iterations. So this isn't enough. Oh, my computer slowed down. Hey, you got a value. It's not an encouraging value, but we got a value. So obviously that's not enough. I think if I let this run, my computer would melt. Is my guess. Though I think this is better. I mean, because I'm guessing these primitive values, pre-computing these for 50 helps tremendous. It's got to. I don't even think this would have came back in 5 minutes, let alone 5 hours. Because if you think of all these values that when we got to 50 iterations, they're immediately picked off. We don't have to compute them. The problem is that with values like these, I'm kind of curious. Again, just playing with data here. If we take that number and we do this has to be multiplied by 2024, right? That's the rule. Yeah, 2024. And so 3, 6, 9, 12, 13. This one's at an asshole, for lack of a better term. 15. So this now would get split. This would get split, but these are 16 digits. It would get split into 8, 4, 2, and 1. So once you get to a power of 16, not a power of 16, once you get to a power of 2 in terms of the size of the number, how many digits are in the number, I should say, you are immediately going to go down to singles. And so you get that benefit as soon as you get to a number that has enough digits that's a power of 2, you will split it out to single digits. So the problem is, well, not a problem, but the thing again with these pre-computes is that these are literally just, if you need to do 25 iterations, a value of 1 will give you these many stones. It doesn't tell you what the values of those stones are. It just says it's going to do about 30,000 stones. So it's kind of a hit and miss thing at this point. If we do these pre-computes for like 30, 35, 40, 45, we can put in as many as we want, but we have to compute them. That's the problem. And I don't want to sit here on a stream and pre-computing all these values. That's not entirely interesting. Well, with the values you're making pre-compute maps, do you know that everything in the map breaks down to something else in the map? I should watch this. For some reason, the chat on my phone, if I have it portrait, the little heart icon, the whatever, shows up and it hides what people are typing. I hate that. If I put it in landscape, then it's fine. But the values you're making pre-commute maps for, do you know that everything in the map breaks down to something else in the map? I mean, I guess 8 doesn't, because 8 goes to... I'm not entirely sure what you're saying, Daniel. I picked these values purely as a guess, because they seem like they were just this very small example. It seems like you're either getting like single digits, or you're getting this 2024, or you're getting the 2024, meaning the 4048. You could get an 8096 as well. But it seems like once you get to these small values, I guess what I could do is, now, we're just randomly trying to hit at certain parts in the process. You could see what I'm getting at, though, is like, what would a 2 produce? What would an 8 produce? A 6, and so on. These would all be multiplied by 2024. And so we could say, well, if you saw that number, And I guess those would be easy to compute, right? I mean, if I want to add those in too, I could, because those are easy to compute. A 2 would always produce the same stone. So a 2 or a multiple of, or the 2 times 2024, they both produce the same value, right? Let's try that out. If I come to my program here and I put this back in and I say, what's 2 times 2024? 4048. Okay. Let's do a different one. Let's do 5 times 2024. So let's put that in here. That looks awful. Get the comma out of there. And let's do one that we've already done before. So this was 5. If we do it for 25, $30, $70, $90. No, it's not the same. No, that's it. What's wrong with my my logic here? If I get a 5 here, on the next iteration, we're going to have a 1024, which is exactly what this is doing. You just don't see it. We get 1 stone. And then, oh, that's right, because we're not actually, we don't do the last thing. Okay, I'm being a little bit silly there. Okay. One is if you had a map that could, in one step, lead you to another map for one more duration, you can make some program that could write pre-compute maps for you for 5 or 25. This should be the same as. Yes. Okay, you're right. 23.8. Yep. It does. Does it really help us out any? I mean, I could say, well, if you're at 24 and 49, but it's the values of what the next iteration would give. And in some of these, you're going to get 2, not 1 stone. So, you know, at what point do you get to be a little bit too cute, and that doesn't really help much. And what I'm doing right now doesn't actually I don't actually keep any of the values of the stones around. I just get the stone count as I'm doing this, because I don't want to keep arrays around as much as I can. It'd be interesting to see I'm telling you from earlier, if you had pre-compute maps for a range of iterations, like from 60 to 70, and going down from 75, you'd be much more likely to hit stuff from the pre-compute maps. I agree. The problem is I mean, if I'm doing it, even if I'm doing it for just one number here, although now I've got the pre-computes in it. So let me just go by your logic here. If I say, let's do, and 0 seems small, but of course we don't know what it does afterwards. Let's say if I did 0 for 60, what does that look like? It takes forever just to compute that. Let me ask you this, Daniel, and I don't want your answer, but I'm just curious. Did you solve this? Did you actually figure out what the answer was for this? Because you're right. If I could get, yes, at least twice. You solved it twice? There are multiple approaches. Great. Now I feel stupid. There's a reason why I call these my random code streams. They're not playthroughs because I'm usually just writing code. I'm doing this as almost like a game stream in a way. I'm trying to do a playthrough, and I typically really do not like looking up answers or cheat codes or anything like that for a game. So that's why I'm really hesitant to ask, for help or something like that. I'm assuming, Daniel, there's a way to do this that's really fast that I'm just missing right now. Or am I on somewhat the right path here? Sure. I love the delay when you're streaming, because you're like, well, what did you mean by that? Which question were you answering? I don't know what sure is answering there. Yeah, just doing 0 with 60 iterations, even with my pre-computes in there, are not helping. It's taking an ungodly amount of time. Yeah, it's funny because the whole thing took 5 minutes. My pre-compute idea is interesting. Lutefisk is interesting, but it sucks. So I appreciate the compliment, but I feel like maybe this isn't even enough. I feel like I'm missing just something fundamentally simple in this. And I don't know what it is that I'm missing. And when I did this in 2022, there were some problems that that you literally could not do as long as it told you to do it. Meaning if you how do I want to say this? If you tried like to say, what would happen if you did this for 1 trillion iterations? Well, if you did it for 1 trillion, it would never stop. It would never come back with an answer. or at least it would take an ungodly amount of time for the answer to come back. And what you had to notice is that there was a pattern where things were being, I think it was like blocks. It was almost like a Tetris thing. And you had to notice that at some point the pattern would repeat. And so then you had to say, well, how big of a length is this pattern? And when does it start? When does it end? And then how many can it fit in there? And then how much would that leave at the top if I get near a trillion? And then you can get the answer really fast. What I'm wondering is, so 0 becomes 1, 20. That becomes 0, 2, twice, and 4. Yeah. If we could figure out a set of values to put in a pre-compute map so that the values for the pre-compute map could be looked up, all looked up in pre-compute maps, iteration n-1. I agree. That would be ideal. I don't know how to do that off the top of my head. There's something noodling in my head though about what you just said that is making me think. What's interesting is doing 60 iterations with just one stone, 0, even with the pre-compute lookups in here, it still hasn't come back, and I don't remember when I ran it. So I am missing something. I am missing something obvious with this to make this so that it's not going to take the age of the universe to figure out. Because this isn't enough. I mean, I'm going to capture this value just because. 60 iterations. 0 stones. And it took 7 minutes just to figure that out. That ain't good enough. That's nowhere near good enough. That's how much? That's 43 billion stones that it has to calculate. And even with my pre-computes in there, that's just simply not enough. There has to be a better way to do this. Unfortunately, I need to stop. I need to stop my stream because I need to get some stuff done, and then I need to go on my little 2-day excursion. So I'll think about this. I'll think about this as I'm on my little excursion and see if anything comes to mind. I'm going to just pause this music here. And there just simply has... I wonder how many different stones that was. It's a good question. I don't know. I would guess that there are repeats in there. And I kind of sort of see where you're going with this. Although I don't know how much benefit that would be. Like, what I'm trying to do is do computes here for ones that I think will show up a lot. These kind of primitive values that everything would eventually deconstruct down to that you would go up to. How often would you see this in the list? Or this? I think the larger numbers you're not going to see repeated enough as much. Yeah, this is like the Collatz problem. It's a very simple iterative problem, but and it doesn't explode out like this either. You can actually put in a very big number, and the sequence doesn't get into billions like this is. So yeah, I don't know. I'm gonna have to. I gotta stop. I have to stop. I don't want to stop, but I have to stop. Can't stop. Won't stop. But I do need to, because I do need to get some stuff moving in the day. So with that, I'm going to finish. Hopefully, as my brain is off of the problem, I can think a little bit more about this one, and see if something comes to mind that's a little bit that somehow makes this computable, and what I would think is a relative. And that's the thing. I gotta think that this is something that can be computable in a relatively short amount of time. If you know the trick, there's this one trick. If you know real life breaks are good. Yeah. And that actually happened with one of these already. One of my previous streams for this is that the getting away from the problem actually helped me to start thinking about different ways of doing it. But there has to be something that lets you compute this in a relatively short amount of time. I just don't know what it is. And I can't think of a way to make that happen. And I do feel a little stupid and not being able to see the answer right away. But something is just not clicking with me on this one. So with that, though, I'm going to stop. So if you're watching, I do appreciate you watching. Please subscribe. I'd greatly appreciate you subscribing to the channel. And I'm trying to get to that 1,000 subscriber mark. So please subscribe. We'd greatly appreciate that. Hopefully when I come back on either Wednesday or Thursday, I have some ideas or something like that. But I will pick it up then. So thank you all for watching. Take care. And I hope to see you in the future.